In our vast, empty universe, nothing is more perplexing to us than the nature and speed of light. Yet one fundamental and deceptively simple question that scientists struggle to answer is, does light travel at the same speed in all directions? This question holds the key to a better understanding of our universe. Is the universe the same in all directions, or is there some directional component we as yet do not comprehend? Einstein proposed a thought experiment. How can we measure the speed of light in any direction? Speed is the time something takes to travel a certain distance. We could, he said, use two clocks to measure the time light takes to travel over, say, a kilometer track. We put one clock at the start of the track and one at the end and measure the time taken for the beam of light to travel between the two. But how do we synchronize the clocks? If we send an electrical signal from the clock at the start of the track to the clock at the end to say the beam of light is on its way, it will take the same time to travel as the beam of light itself. So the experiment won't work. What if we synchronize the clocks before we take the second clock to the end of the track? Well, Einstein's theory of relativity states that time runs differently for objects traveling at different speeds. Again, therefore, our experiment will fail. We can't ensure that the two clocks are still synchronized. Perhaps the only way you can measure the speed of light, therefore, is by using one clock and timing the beam of light over a round trip starting from and returning to the same clock. For example, we could bounce the beam of light off a mirror. But of course, this assumes that light travels the same in all directions, and that is very thing we are trying to discover. The assumption that light travels at the same speed in all directions is called Einstein's synchronization convention. It assumes that the speed of light is constant, regardless of direction. This assumption, however straightforward it seems, has profound implications for our understanding of the cosmos. This convention isn't about physically setting clocks. It's about establishing a framework to measure time and space in the universe. It's about understanding the very fabric of reality. The speed of light, denoted by the letter c, is approximately 299,792,458 meters per second. That's incredibly fast. But is it the same in all directions? Einstein's theory of special relativity hinges on the idea that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This principle, seemingly counterintuitive, has been experimentally confirmed numerous times. However, confirming that light travels at c relative to any observer doesn't automatically mean it travels at c in all directions. Could there be subtle variations undetectable by our current instruments? This is where the debate gets interesting. If light doesn't travel at the same speed in all directions, the universe might not be as symmetrical and uniform as we think. It could challenge our fundamental understanding of physics. The idea that light travels at the same speed in all directions is not just a hunch. It's supported by a mountain of experimental evidence and forms the bedrock of modern physics. One compelling piece of evidence comes from experiments with particles called pions. Pions decay, emitting two photons, or light particles. These photons are always observed traveling at the speed of light, regardless of the direction of the pion's motion. This observation strongly suggests that light's speed is independent of direction. Furthermore, Einstein's theory of special relativity, which relies on the constancy of the speed of light, has been rigorously tested and confirmed for over a century. From particle accelerators to GPS satellites, its predictions have been consistently validated. The success of special relativity in explaining and predicting physical phenomena lends strong support to the idea that light travels at the same speed in all directions. While the evidence for the constancy of the speed of light is strong, some observations challenge this assumption. The Planck length, an incredibly small scale, is significant in modern physics as it represents the smallest measurable length. It is defined to be constant. However, experiments involving high-energy particle collisions have hinted at potential fluctuations in the Planck length. At quantum levels, therefore, the very fabric of space-time itself may fluctuate, causing the Planck length itself to vary. These fluctuations would require changes in the speed of light to maintain the consistency of the Planck length. Another example is the cosmic microwave background radiation, which has unexpected fluctuations. And some cosmological observations, like the distribution of galaxies, are difficult to reconcile with a uniform speed of light. These anomalies strongly suggest our understanding might be incomplete, and the Planck length could hold the key to new physics. Observations and experiments in quantum gravity and string theory suggest that under certain conditions, the Planck length could vary, opening new avenues for exploring the nature of spacetime. The question of whether light travels at the same speed in all directions lies at the heart of ongoing debates in physics. It's a testament to the dynamic nature of science, where even the most established theories are constantly challenged and refined. On one hand, we have the elegance and predictive power of Einstein's theory of special relativity, supported by a wealth of experimental evidence. On the other hand, we have intriguing anomalies and alternative theories that suggest the universe might be more complex than we currently understand. This tension between established theories and new observations is the engine of scientific progress. It drives us to ask deeper questions, develop more precise instruments, and explore new theoretical frameworks. The quest to understand the nature of light and its speed is far from over. It's a journey of exploration and discovery, pushing the boundaries of human knowledge. Discovering that light doesn't travel at the same speed in all directions would be profound. It could challenge modern physics, requiring us to rethink space, time, and gravity. It could also have far-reaching technological implications. Harnessing this variation could revolutionize communication, computing, and space travel. Imagine sending information faster than light or traveling to distant stars instantly. These possibilities highlight the impact of fundamental discoveries in physics. The exploration of the universe is a journey driven by curiosity and the pursuit of knowledge.